Okay, we start to talk about the urinary system today. So we're going to talk about urinary. Anatomically, it's pretty simple. There's some physiology involved, which we'll have to talk about to some extent. And then we can talk about reproductive. So, anatomy of the urinary system. Major organs, 2 kidneys. As a very good friend, family friend, doctor says it, there is a reason God gave us 2 kidneys. If one fails, we have another. Left kidney is a little bit higher, okay? They are retroperitoneal. If God forbid you feel the flanking pain located closer to the back, it may be the urinary tract infection that migrated all the way up to kidneys. So be aware. You have to know where the kidneys are. Kidneys receive a lot of blood supply. You can tell. This and this are the left and right renal arteries. You see that these arteries are pretty considerable in size. Kidneys receive about 25% of cardiac output. You have to understand, does anyone know what is the percentage of blood that brain receives? But 15% of blood goes to the brain. 15% of cardiac output goes to the brain, quarter goes to the kidneys at rest, and about quarter goes to the liver. You can understand brain with thinking. You can understand liver. It's metabolically active tissue that does a lot of biochemistry. But why kidneys? Why kidneys? What do they do? Huh? Somebody said filter. That's right, they filter. That's the whole purpose. Okay? And you will see that actually they consume quite considerable amount of energy. Does that make sense so far? We're good? So they are supplied by renal arteries, drained by the renal veins, and you can see renal arteries stem directly from aorta, and renal veins, they drain directly into the inferior vena cava. Kidneys, when they produce urine, they do produce urine. Urine is drained into the ureters, long, elastic, muscular tubes that lead urine to the urinary bladder. Basically, a muscular bag, which squeezes when we urinate and pushes urine through the urethra and urethral orifice outside. Renal arteries, renal veins, ureters, all the nerve supply that goes to the kidneys, they all enter kidneys at the hilum. We have seen hilum as the element of a structure before. Hilum is where? Huh? Lungs, perfect. Lungs. I thought about lymph node, but no, perfect. Any depression where vessels, nerves enter the organ, it's a hilum. Okay? And some other features. Adrenal glands, adrenal, above kidneys. Okay? You can see them there. And yeah, adrenal glands have nothing to do with kidney function directly. They just located there. Now this is the transverse section of the abdomen. You can see white peritoneum. Okay, and you can see that kidneys are definitely retroperitoneal. Each kidney is surrounded on the outside by the fascia, renal fascia. Okay. Then under the fascia there is the fat capsule. It cushions the liver. And finally they bounded by the fibrous capsule. If I would have a chance, so that's fibrous capsule, if I would have a chance to bring you a mouse and we would dissect the mouse, we would see that when you isolate kidneys, it looks like each kidney of a mouse is surrounded by thin, almost transparent film. This is a mix of fat and connective tissue that surround each kidney. When we used to collect kidneys from mice, you cut the kidney and then you take a cotton swab and you slide it on top of the kidney, collecting that connective tissue, because you need a pure kidney as an organ. So let's take a look at the in the inside. I'm going to show it on the image, and I'm going to use the model. Does everybody see the model? Kidney is a lot of parenchymatous organs without any cavity. Consists of two distinct layers, outer cortex and inner medulla. So this is the cortex. See that? And this is medulla. On the image, that's going to be cortex, the lighter cortex, and the darker medulla. So that's medulla. Right? If you would look at the structures of cortex and medulla, you will see that medulla is organized in almost triangular structures. These triangular structures are called renal pyramids. And each pyramid culminates in, so the top of the pyramid is called renal papilla. Okay? Basically, renal papilla is the place where urine is draining from initially. Does that make sense? It's just a place. Don't take it as like some super important structure. It's just a place. We call this a renal papilla. Now, renal pyramids are separated by renal columns. Now, renal columns are extensions of cortical tissue. So this here is the renal pyramid. This is the renal column. Can you see it? Fantastic. What I want you to say about that. Oh, if you look at the picture, not just at the picture, at the photograph of the actual kidney dissected on the left, this one, you can see the anatomical difference, like difference in appearance between the cortex and medulla. It turns out these two layers, not only anatomically distinct, but also functionally distinct. So what produces urine? Both cortex and medulla, of course, they both participate. Okay, medullary tissue is really important in regulation of the urinary concentration. You know how when you drink a lot of fluids, your urine becomes transparent and diluted, and if you dehydrate it, it's really dark and really concentrated and the volume is small. That makes sense? And overall, both cortex and medulla, they participate in the urine formation. Am I clear? So what is the pathway for the urine drainage and formation and drainage in the kidney? Now look at the right side. I'm going to draw it there. So urine is formed somewhere here. When it is formed, completely formed, it's ready to go. through the renal papillae from the renal pyramids. It enters this empty pocket that is called minor calyx. We clear? Now, urine from all these minor calyces drain into bigger major calyx. And then from major calyx, it enters the renal pelvis. That makes sense? So, renal pyramid, minor calyx, major calyx, renal pelvis. Typical question. Can you draw the line between those three? And are you going to ask us to distinguish between these three on the anatomy exam? Absolutely not. Okay? Well, let me be completely clear about it. If I point here and ask you what is this space, you tell me it's renal pelvis. I'm not going to ask you to say, is it renal pelvis or one of the major calyces? No. But, you know, like if it's, you have to know that it's not a minor one. Am I clear? I will be very, and if you want, you can ask me a question and I'll point at it specifically. Good? Okay. And from renal pelvis, urine enters the ureter. That makes sense here. Good? So, let's talk about urine formation. This is absolutely fascinating process. I usually, you know, I'm a sucker for analogies, so I compare it to the cleaning effort at home. You know how sometimes it happens, you come home and you're just tired of all the shit that you have in all like dressers and drawers and cabinets and yeah, I know. You just need to throw it away, you just feel like it. And you come home and you quite literally take all of it, I mean everything. You just clean up everything, put it in the trash bags, and put it in the garage and it's Friday and the trash collection is on Monday. So it's ready to go. Your house is pristine. And then you think, maybe it's not such a good idea. Maybe I need something to wear, you know, something to cook on. So go back to those. So that process, when everything gets thrown away, is called filtration. I'll come back to the structures, okay? Infiltration. Everything from plasma, except cells and proteins, all this small stuff, like you're not throwing away the furniture, you know? You're not throwing away the toilet bowl, okay? So, all small stuff, ions, carbohydrates, amino acids, various small organic chemicals, they all go from the blood to filtrate. Does that make sense? Okay. Then you think, I probably need some stuff from what I just threw away. So you go in the garage and you start to carefully pick what you need. Say you look at the box with skillets and you look at it and say, I probably don't need 27 skillets to cook on. I just need 3. And you pick all 3 and bring them back into the kitchen. Then you look at the bag with pence and think, I have 1 pence and there's 1 pence in the bag. I probably could use spare pence. So you take all pence that you threw away, 1 pair, you take them back. Does that make sense? So you go through that and you find, I don't know, something and you bring it back or not. So this process of bringing back what you need is called reabsorption, number 2. So you see the direction is from filtrate into the blood. Does that make sense? And then you look at what you brought back and look at this and think, I probably do not need 27 Van Halen CDs. I can live with greatest hits. And you live greatest hits and throw away the stuff that you actually don't need again. This is called secretion. Basically, you go through 2 rounds of throwaway and 1 round of return. Your kidneys throw away things during filtration, collect some of them back during reabsorption, and do another round of cleanup during secretion. Am I clear? Good. Now, structurally, where does it happen? The elementary unit of a kidney, working unit, is a nephron. We have about 1 million nephrons in the kidney. Nephron shown in the right. It's nephron. This is nephron. They're really microscopic. So this is the nephron. This is the nephron. And this is the nephron. I have actually 2 nephrons here. Okay. So there are glomeruli of the nephron. This is glomerulus of the nephron. This is glomerulus. Then you have nephron tubule. And generally, part that is not considered to be a nephron, collecting duct. So if we come back to the process of urine formation, what happens is, look at this, blood flows through the blood vessel, enters the capillary in the glomerulus, filtration happens here, filtration happens, whatever is filtered enters glomerular capsule. From glomerular capsule, filtrate, it's not urine yet, filtrate, flows into the renal tubule. Renal tubule has 3 very distinct parts: proximal, nephron loop, and distal convoluted tube. So it flows through the tubule where reabsorption and secretion happen, and by this moment right here where the proximal convoluted tubule enters collecting duct, it is almost urine. There is a little part of reabsorption can happen in the collecting duct once it gets all the way down to the medulla. So here, this model, this upper portion is cortex. It's lower in the medulla. So when the collecting duct is deep in the medulla, it approaches renal papilla and the fluid starts to drain. Does that make sense? Good? Okay. Any questions? We process a lot of fluid. Daily, we process about 180 liters of actual filtrate. So we form 180 liters. If you prefer imperial units, something like 50 gallons of filtrate a day. And we produce less than half a gallon of urine a day. It depends, don't get me wrong. The amount of tea that I drink is enormous. So you drink more, you produce more urine. You drink less, you produce less. So far, we're clear. So let's talk about nephrons. We have two types of nephrons. Cortical, shown on the left, and juxtamedullary, shown on the right. Cortical, what does it tell you? Where are these nephrons? There you go. I mean, there's a little part, the nephron loop, which descends into the medulla, but the majority of the nephron is in the cortex. Juxtamedullary. Medulla. Juxta, what does that mean? Next to. Yes. So next to, it's like almost entirely in the medulla. Look at this. It has an enormous nephron loop, okay? And convoluted tubes and the glomerulus are located in the deep cortex, very close to the medulla. That makes sense? So they have two very distinct functions. So cortical nephrons, here, they will be responsible for typical kidney things. There will be filtration in the glomerulus, okay? Reabsorption in the proximal convoluted tube, okay? And then not much secretion and reabsorption in the nephron loop, and a little bit of secretion and reabsorption in the distal convoluted tube. Now you may ask the question, you should actually. This secretion reabsorption thing, where does it go to? Let's draw it a little bit. So this is the blood vessel. This is tubule, so filtrate. Okay? During filtration, fluid, where does it go? From where to where? Blood tubules. During reabsorption, chemicals, where do they go to? From back into the blood. Now, this back into the blood thing, do they like hop from filtrate straight into the blood vessel? You have to understand that when we say into the blood, it's actually first in the extracellular fluid and then into the blood. Does that make sense? So they will go into the extracellular fluid first and then into the blood. Filtration is different. Filtration, there's no extracellular fluid step. We'll see it so far, more or less. And then secretion. Final bout of throwing things back in the filtrate. That makes sense. Go ahead.
Is the reason why it goes back into the other one from the blood twice because it goes through the extracellular fluid?
Not really. It's a great question. Not really. Mostly it's the fine regulation of certain ions. Since you brought up this question, I will give an example. Remember our old buddy aldosterone. Remember? Mineralocorticoid. What does it increase? Actually, it it will increase retention, so it will decrease urine production by sodium retention and water retention. What does it give filtrate in exchange for sodium? It increases secretion of another ion. Starts with P, potassium. Now, potassium concentrations in the extracellular fluid, are they high or are they low in the extracellular fluid? Rule of thumb, sort of a side note. 3 ions that are higher in the extracellular fluid. Sodium, calcium, chloride. Ion that is higher in the cell, potassium. Now, you eat a pound of bananas, which are incredibly rich in potassium. What's going to happen to your blood potassium levels or ECF potassium levels? They're going to spike right away. And that's terrible. Because homeostatically, your extracellular potassium levels should be maintained low for the nerve signal transmission, cardiac function, blah, 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 blah. When potassium spikes, aldosterone is elevated and stimulates potassium secretion. So secretion is mostly for the fine-tuning of concentrations. Did I answer your question? Good. Juxtamedullary nephrons. You see how big they are? They're also surrounded by this network of capillaries. Okay? So this network of capillaries is called vasa recta. Vasa meaning blood vessels, recta meaning straight. Now the function of juxtamedullary nephrons is to exclusively regulate the concentration of a filtrate. Do you understand what I'm trying to tell you about the function? So again, cortical nephrons, they will produce filtrate. Essential chemicals will be reabsorbed from the filtrate. They will come back to so-called peritubular capillaries, and then there may be secretion. So they will be, for instance, do you have glucose in your blood? Or in your urine? I hope not. I hope not. You shouldn't. You shouldn't. Well, if I will eat like an entire carrot cake, will I have glucose in my urine? I may. Actually, I may. It's possible. Okay? But basically, what I'm trying to tell you is that glucose is filtered out, but we reabsorb it completely because we need it. Does that make sense? So that glucose reabsorption, amino acid reabsorption, sodium reabsorption, potassium, calcium, magnesium, all that crap, all of it happens in the cortical nephrons. The work for juxtamedullary nephrons is to regulate concentration of filtrate. If I'm drinking 2 gallons of water, well, not even 2, it's probably too much. 1.5 gallons water a day, juxtamedullary nephrons will make sure that I'm not swollen. So they will get rid of an extra water. Does that make sense? If I'm dehydrated, they will make sure to keep water inside. Is that clear? So essentially, you can think of it this way. When reabsorption happens, all that is being reabsorbed is picked up by peritubular capillaries, and it's brought back into the circulation. Am I clear? Few words we're going to start, but we're not going to finish. Few words about the structure of the glomerulus. So this is a typical glomerulus, and this here is the typical glomerulus. Okay. So in this one, what you can see, let me show you on the model as well as on the image. So first of all, blood flows into glomerulus by afferent arteriole. This one, I'm holding it. Blood leaves the glomerulus via efferent arteriole. This one. What can you tell about these arterioles that's very noticeable? Afferent's bigger, yeah. Oh, by the way, what are these? Yeah, isn't that weird? How capillary bed should be organized? Arterial, capillaries, venule. That's the only capillary bed. We have arterial, capillaries, not arterial. You will see it's really important. Now, what's the difference? Very big functional difference between arterial and venule. Arterial has certain type of tissue. In this case, it's not so much about oxygenation, it's about ability to do something. Yep, constrict and dilate. Venules cannot do that, arterioles can. So essentially, you have a capillary bed here that has incoming vessel that can constrict and dilate, and outcoming vessel, draining vessel, that can constrict and dilate. That makes sense? Now, since incoming vessel is big and draining or efferent arteriole is smaller, what can you say about the pressure in the those capillaries? It's pretty high. Okay, it's pretty high. So you see that actually the pressure at the site of entry is higher than the regular pressure in like any other capillary bed. Okay, so that creates, now if you would look at the pressures that contribute to the filtration, and I just want to introduce you to this. So this is hydrostatic pressure in the glomerular capillary, which is 55 millimeters of mercury. Okay? This on the bottom is the hydrostatic pressure in the glomerular capsule, which contains filtrate. So here in the capsule is filtrate, future urine. Okay, you can see that capillary pressure in the capillaries is higher. But here's the deal. Cells and proteins cannot get from the capillary into the filtrate. Does that make sense? So we can put a sign here, no proteins. What is the role of proteins like albumin in the blood? What type of pressure do they create? It starts with O, osmotic pressure. So if you have proteins on one side of the membrane, inside of the capillary, but no proteins in the filtrate, then proteins in the blood will draw the fluid back into the capillary of glomeruli. Does that make sense? So essentially you have three pressures acting here. You have hydrostatic pressure, that is from the blood in glomerular capillaries, hydrostatic pressure from the filtrate, and osmotic pressure that is induced by albumin in the blood but draws fluid back into the capillary. The net filtration pressure in the glomerular capillaries is 10. again, you know I hate numbers, like meaningless memorization. And I can ask you, what's going to happen if okay, let's play. Your albumin concentration in the blood goes up. You dehydrate it. Which pressure is going to increase? Albumin in blood goes up. Everything else stays the same, but albumin goes up. Albumin is responsible for which pressure? Osmotic. So that osmotic, that purple arrow, increases. What does that mean? Less filtrate is formed, right? You pee less, essentially. Your blood pressure goes up. Which pressure is going to increase? The first row, the hydrostatic pressure in the capillaries. How is it going to affect the filtrate formation? Yeah, you're going to form more filtrate. You know what? If your blood pressure is very high, think about this. You have a pipe that is normally fitted for certain pressure. If your blood pressure is high all the time, then that extra pressure will damage the glomeruli. And we'll talk about how it affects kidney function and how it can lead to kidney failure next time.